Welcome to the IEEE PELS educational videos. The title of this presentation is High Frequency Effects in Transformer Windings, and I would like to begin by thanking Sandun Karupu and Jorge Vega who invited me to put this presentation together. So without any further ado, let's begin. Okay, so here basically is an outline of the presentation. We're going to split out the losses in a typical transformer in terms of the copper losses, skin effect, proximity effect. Then we're going to look at how can we optimize the winding to minimize these losses. Then we're going to look at some mitigation factors in terms of using Litz wire, interleaving, and finally we're going to look at a fringing effect, which is really something that's come into play in the last couple of years, particularly now with the advent of resonant converters. Okay, so here we can see a basic transformer winding, and what we have is we have losses in the core, which are fundamentally hysteresis losses and eddy current losses. Now, the thing about the core losses is we can minimize those by equating the core losses with the winding losses. That's a well-known principle. But for the purpose of today's presentation, once we've achieved that optimization, I want to now concentrate on the windings and in particular the sources of losses there, skin effect and proximity effect. So let's move on a little bit. Right, in this picture here we can see there are basically three different effects in the winding. There's the skin effect, which is essentially the losses in a single conductor. There's a proximity effect, which arises because of the interaction between two windings or two layers of windings. And then the third option or possibility is the fringing effect. And the unusual thing about this is that it's really an interaction between the gap in the core of the transformer and the nearby windings. So again, now let's take a closer look at these. We'll start with the skin effect. Now the skin effect essentially is a loss that pertains to a single conductor. And here we can see it in graphical form. We have a solid conductor and the magnetic field increases from 0 at the center, maximum at the outer circumference, and then it tails off outside the conductor. Looking at it from the side, we can see here we basically have a conductor with current going through the conductor. In this case the current is current I. Now because the magnetic field is generated by that current in a circular fashion, it will create its own eddy currents in accordance with Faraday's law, which will attempt to counteract that magnetic field. And using our right hand rule, we can see that the eddy currents flow up the outside and down the center of the conductor. Now remember, it's a bit like water flowing in a pipe. Whatever goes in one end has to come out the other end. So we don't change the net current, but what we are going to change is the distribution of that current. So we can see that by looking at the current density picture here. And you can see the net effect of the eddy currents is to reduce the current density at the center and increase it at the outside, while recalling that the total is still current I. Perhaps we can look at it in more detail here. Here's a typical copper conductor cross section. Here's the center and here are the outsides. So at low frequencies, in this case 1 kilohertz, the current density is constant across the conductor. If I increase the frequency now to 10 kilohertz, we're going to suppress the current in the middle and increase it on the outside. And then when I go to 100 kilohertz, that phenomenon becomes more dominant. And finally, when I look at 1 megahertz, you can see that all the current is on the outside here and there's no current in the middle. So in all intents and purposes, we could use a hollow conductor here. And this outside edge here is called the skin depth. So it's really a measure of the thickness of the outside layer where all the current flows. We can probably see it a little bit better in the next slide. Right, so here's the current density distribution at 10 kilohertz, evenly distributed around the conductor. At 100 kilohertz, we're starting to bunch the current to the outside. Red means high current density. And then on the 1 megahertz, you can see that the current is in a very narrow layer on the outside here. And the thickness of that red layer is effectively the skin depth. So at 1 megahertz, you can see that the skin depth here is a lot smaller than the radius of the conductor. Now, the good thing is we can analyze this analytically, and in actual fact, we can plot the results. So here we have the AC resistance divided by the DC resistance. Now, you can see that if I take the ratio of the radius of the conductor to the skin depth, then we have at that rate, when that ratio is equal to 1, effectively the AC resistance and the DC resistance are roughly the same. But once we go beyond that, the effect is to multiply the AC resistance over DC resistance. And the reason for that is very simply, we effectively have the current flowing in a smaller area, which by definition increases the resistance. So what is the skin depth? Well, the skin depth is a function of the conductivity of the material, and so we're mostly dealing with copper. We can use the constant for that. And the other factor is the frequency. And obviously we can see that in the picture here. As we increase the frequency, the skin depth gets smaller. And indeed, it's proportional to the square root of frequency. Now, if I'm designing a conductor in a transformer, essentially I don't want an AC resistance that's several factors bigger than the DC resistance. So quite often we'll be dealing in this region down here where the AC resistance may be 2 to 3 times bigger than the DC resistance. And we have a nice simple analytical formula here to work that out. And it's a function of the ratio of the radius of the conductor to the skin depth. So we can calculate that in any given situation. Just to point out, worth mentioning here, and this is true in all magnetic circuits, when the physical dimension becomes comparable to the skin depth, we're going to start running into problems with AC losses. So as a first rule of thumb, we want our physical dimension, in this case the radius of the conductor, to be less than a skin depth. Okay, so let's just move on now and look at the proximity effect. A little bit more complicated, but the principle is the same. Essentially, now what we have here is we have a 2-turn primary in the transformer and we have a 3-turn secondary. Now, if we take Ampere's law and apply it around this loop here, C1, effectively the magnetic field here is related to the current inside the loop, so that's 1 unit. If I take C2, which encompasses or encloses 2 units of current, then the H field, the magnetic field, will be twice as big. And I've plotted this here. Now, when we go to the secondary, the current is in the opposite direction, so it'll subtract from what was there already. And since there are 3 turns in the secondary, we'll decrease it in 3 steps by 1/3, 1/3, and 1/3. Now, if we look at it a little bit more closely, excuse me, essentially we have a higher magnetic field here than we do here. This, in fact, in this case is double that value as we predicted. And essentially the eddy currents will flow to prevent the magnetic field inside this conductor. And it'll flow in the direction that I've indicated here to block the magnetic field. And if we now examine the eddy currents will be high on the outside and effectively 0 in the middle of the conductor. And it might be easier to see it here in the finite element picture. Essentially, we have low magnetic fields here and low current density because we've only got 1 turn here. As we increase the number of turns, we increase the current density due to eddy currents. And you can see that the highest value is between the primary and the secondary here. Red, again, being the highest. So we need to look at this now more closely, and in order to analyze it, it was analyzed by Dowell, famous Dowell's formula back in 1966. Essentially what he did was he modeled this as a cylinder and took the magnetic field on either side of the cylinder and worked out the AC losses due to the current flowing in the cylinder. And then he came up with this plot, and essentially it's a function of, here we have delta, which is the radius of the thickness of the conductor in this case to the skin depth, and here is the effective resistance due to the eddy currents, and over here we have the number of layers. So in this case the primary P is equal to 2 layers or 2 turns, and the secondary would be P equal to 3. Now again, we notice that once the physical dimension becomes comparable to the skin depth, we're going to start seeing an increase in AC resistance. Now again, there's no way we're going to start designing a winding that has an AC resistance 100 times the DC resistance. Notice the log scale here. So effectively, for good design practice, we're going to be concentrating down here, where the AC resistance may be 2 or 3 times bigger than the DC resistance at the outside. And luckily, we have a nice simple formula for that region. So the effective or AC resistance to the DC resistance is related to the number of turns or layers, and delta, the ratio of the layer thickness to the skin depth. So now that allows us to do the calculation, or we can of course read it off the graph. Right, now of course we're not quite there yet, because unfortunately in power electronics we're never dealing with pure sine waves. We're dealing with square waves and triangle waves. So what we're going to do is we're going to take this formula, this approximation, and we're going to apply it to each harmonic in the AC waveform that appears in our power electronic circuit. So here's our Fourier series. We have a DC current and we have harmonic components here. And the power loss then is related to the DC current and each of the harmonics. And we can apply Dowell's formula individually to each one of these harmonics. And without getting into any great detail, we can use our approximation, and we have a nice clean formula here that's related to, again, the number of layers or turns in our winding and the RMS value of each of the harmonic currents. Now, we're not quite there yet, because the trouble is we need to come up with a Fourier series for each of these power electronics waveforms. And while we might know what it is for a triangle wave or a square wave, the reality is in practice, power electronics waveforms are neither of these. They're approximated by them. So we need to go one step further. Now, let's look at this graph here first. Essentially, this is a plot of the effective resistance due to all the harmonics, as we've calculated in the previous slide, and the thickness of the winding layer that we're talking about. Now, if we go for a very thin winding layer, clearly the AC resistance is going to be very high, simply because we have a very small area for current flow. Now, as we start increasing the thickness of the layer, or the winding, then what's going to happen is our resistance is going to decrease, simply because we have more winding area for the current to flow. But then we reach a point here, roughly, where the skin depth and the thickness of the foil or winding is comparable, and as I said already, that's when the eddy currents kick in, and once they start kicking in, the AC resistance is going to increase. But the nice thing about it is there's a point here where the AC resistance is minimized or optimized, and that's the point we want to operate at. This curve here contains several values of P from 1 layer all the way up to 10 layers. Now, in order to generate this graph, we have to take the Fourier series, take each of the harmonics, calculate the effect due to in Dowell's formula, add up all the components in our power loss, and then plot this. Quite a cumbersome task, and as I mentioned already, we would have to do it for every single waveform. If the duty cycle changes, we have to regenerate it, and so on and so forth. But thankfully, and there's a different way to do it and an easier way to do it. And if you just bear with me, a small little bit of mathematics here. Here's our Fourier series, And if we take the RMS value of that, we just take the DC value and each of the harmonics. And we're using square values here just to avoid using the square root sign. Now, if I take the derivative of this, the omega will go on the outside and we'll have a sine function. And I can also take the RMS value of this by now just taking each of the harmonics. And you notice now the harmonic number n appears here because of the derivative. So, on our previous slide, we took the AC power loss in terms of the DC current and the harmonics and used Dowell's approximation. We had that already. But now, if you look carefully, this piece of it here corresponds to the IRMS, and this piece here corresponds to the derivative of IRMS. And if we put the two of these in here, we end up with a very neat formula that says our effective resistance to our DC resistance is simply a function of the number of layers, the RMS current, and the derivative of the RMS current. And that represents an approximation to the curve in the area of this minimized point here. And finally, at the optimum point, the AC resistance to the DC resistance is simply 4/3. So the beauty of this is we don't have to come along and find each Fourier series. All we have to do is calculate the RMS value of the current and the RMS value of its derivative, which we can do graphically. It's not difficult. Maybe it's easier to see it in an example. Here's a push-pull, and we have a rectangular waveform in the primary, and we can't use an ideal rectangle here because in reality there's a rise time and a fall time associated with the current, but that rise time and fall time will give us a derivative waveform here. So here's the RMS, here's the waveform, and here's this derivative. Now, there are lots of mathematical tables that will give us the RMS value of this waveform, and likewise, we can calculate the RMS value of the derivative quite easily here. So, I've taken now my formula for the optimum delta. I've put in the RMS value of this current waveform and its derivative, quite easily done. And I've actually, one of my students has produced tables, so we can do this for lots of different waveforms. We happen to be dealing with a 50 kilohertz waveform here, so the skin depth is related to the square root of frequency, and in this case it's just less than 0.3 millimeters. Our optimum layer based on our new formula is 0.33. So if I take my skin depth of 0.3 and combine it with my optimum layer thickness, I end up with a foil thickness of 0.1 of a millimeter. Now, I just want to mention that we actually have a power supply that we built with a foil of 0.1 millimeter, and indeed the losses were optimized. So this is based on an actual working power supply. Okay, so that's quite helpful, but we're not out of the woods yet. So maybe we can't always use a foil like this. Maybe we want to stick to our solid conductor. Now, this solid conductor for our push-pull example is exactly the same area as our foil. So, and for the foil, we know that our effective over RDC is 4/3, which is roughly 1.3. Now, if I take the skin depth of my solid conductor, and we had a formula for that, we can work it out, a nice simple formula here, and it turns out that to be 1.95. In other words, the skin depth here creates AC losses almost double the DC losses. Whereas here, with the proximity effect, we've only increased the losses by 30%. So clearly, there's no difficulty choosing the foil in this case. But supposing we can't use a foil, we could still deal with a round conductor, but instead of having a conductor like this where the skin depth is a lot less than the radius, we've split this up into lots of round conductors, which we now call strands. And that gives us what's called a Litz wire. Okay, well that's the end of the presentation. I hope you enjoyed it. If you have any questions, I'm more than happy to take questions via email. My email address is wghurley@ieee.org. And if you would like to interact or ask any questions, I'm more